Recording is starting now. Last time we were almost finished looking at logarithms. So one of the things that we looked through in the last class was expanding logarithms. And I just want to do one more example to remind you about that before we move on to, the change of base formula, using logs to solve exponential equations and solving logarithmic equations. And once we're done with those couple of kind of things that I picked, we're moving on to trigonometry then. So, okay, one example, kind of a reminder from last time. Let's say you're asked to expand the natural log of 4 times e to the 2x times x plus 1 divided by x minus 3 to the power of 5 by e to the x minus 1. Okay, so only in this course, I think, will you ever see a question in an exam where you see something phrased like expand this logarithm. This is just us developing the skills of working with the log laws, and you'll probably see it in your assignment and maybe your final as well, a question like this. But when you go to calculus, it won't really be like, the question won't be expand this, it'll be differentiate this. And to differentiate that as it looks right now in calculus will be awful. It's a lot of things to do at once. I know that some of you have seen calculus already. So in this, I'm seeing differentiating log using a chain rule, using product rules, using quotient rules, all mixed up together, and it's nasty. But with a couple of steps like we're going through over in this course, just knowing your log laws, you can make that differentiation a lot easier. So that's kind of why we're practicing these. Okay, so first line of this, if you remember from last week, is to do the log of A over log of B rule. You know what, since we're refreshing it, I'm going to just write each of the log laws that are coming up before we do it. So the first thing I'm looking at is that I have like a log of A over B rule, and that's going to be log of A minus log of B. That was actually what I intended to write in that quiz question, but I accidentally had an equal sign on the second one instead of a minus sign. So that's why everybody got full marks for that option to select, because I made a mistake. But applying that rule to this situation, what I'm seeing now is the natural log of 4 e to the 2x by x plus 1 minus natural log of x minus 3 to the power of 5 by e to the x minus 1. That's the first one that I'm seeing here. The second one is you're going to use that product rule of logs, the one that's a different pen. I guess I'll use the same pen. It's the one that looks like this. Log of AB equals log of A plus log of B. Now, if you remember in that question, in question 4, the option that I had given you, which was wrong, was this one here. If anybody selected that as a correct rule of logs, that's a question you got wrong then. That one is not correct. It's the one above. So even though it looks kind of same, you're kind of thinking, oh, it's multiplying and stuff. It's not the same thing at all, and you have to be careful that you don't apply a log law to something that there is no log law for. So this one here is wrong. That was something that came up in your quiz. But we're going to apply this product rule, and it's not just limited to just 2 things inside the log multiplying. If I have log of A, B, C, D, for example, that's log of A plus log of B plus log of C plus log of B. So it can work with any number of things multiplying as long as they're all inside the log function, okay? So that's going to be our next step in this. So I'm seeing a couple of products here. I'm seeing like an A a B, and a C. Over here, I'm seeing like an A and a B. So I'm going to be applying that product log rule into each of those logs and adding them all up in this way. So here I see natural log of 4 plus natural log of e to the 2x plus natural log of x plus 1 minus, and it's a good idea to open a bracket here because that minus sign in front of the second log term is going to apply to everything that comes out of this rule that we do. So it's going to be natural log of x minus 3 to the 5 plus natural log of e to the x minus 1. So next up, we can use the rule. Okay, sorry, I was rewriting the rules each time, wasn't I? Next up, we can use this rule that looks like this. If you have log of something to a power of p like that, that is the same as p log a. Okay, so we can bring any of those powers down to multiply in front instead. Oops. So this is still just natural log of 4, but this is 2x times natural log of e plus natural log of x plus 1 minus 5 times natural log of x minus 3 plus x minus 1 times natural log of e. So this here doesn't look like it, but that's a bracket. That's it. We're almost finished. Anything else I can do here to simplify this a little further? Anyone know what I can do? Do we not know, or are you asleep still? Okay, nobody seems confident enough to suggest something here. One thing that we should notice as well before we just say, okay, we're finished, is that the natural log of e is equal to 1. That happens over here. So if you remember, one more log law that comes up that we can use here is log to the base b of b is equal to 1. That means that log to the base 2 of 2 would be 1. Log to the base 7 of 7 would be 1. Now natural log to the base e of e, or what we normally write it as, would be natural log. That's the same base right there. That's equal to 1. It's just that we use this notation so it can get forgotten sometimes. So don't forget that natural log of e is also equal to 1. So we'll just rewrite our final answer here. Natural log of 4 plus 2x plus natural log of x plus 1 minus 5 times natural log of x minus 3 plus x minus 1. And actually we can do a little bit more still because we have a 2x plus an x here. This is natural log of 4 plus 3x plus natural log of x plus 1. Oh, I made a mistake, haven't I? Yeah, I did. Look what I did. That was supposed to distribute. I should have distributed by minus sign. And that would be minus x plus 1 after I distribute. So I did make a mistake there. That means that this is not 3x. It's actually 2x minus x, which is x. 5 times natural log of x minus 3 plus 1. That would be our final answer. Okay. What about this here? Can something be done with that? What is that? Natural log of 4. Anybody in the chat? What would that be, roughly? 2 squared. Oh, right. Oh, I see what you're saying. So what I could do is write this as this. Yeah, I could definitely do that. I could use that power law. Eric is saying 2. What would it roughly be? That to me, when I see that as a number. I see that as a number somewhere between 1 and 2, maybe a little bit closer to 1. So remember what we're doing here. If you see something like this here, what comes into mind is that what this actually means is log to the base e of 4. So remember what I think? I think e to power of what makes 4. That's what you kind of think of mentally when you see it. Now e, if you remember, that's about 2.7. So 2.7 to the power of what is equal to 4? Well, 2.7 is close to 3. 3 squared is 9. So making that 2.7 a little bit smaller, it's hard to know exactly. I would guess it's a number between 1 and 2. I'd probably guess it's like 1.5 maybe, or 1.4. I don't know. I can't do that in my head. But when I see natural log of 4, all I see is a number. Just some number that I see it in the exact same way as I see 1. I look at that, and I say they're the same type of thing. 1 plus 1.5 or something, probably 2.5, but I don't know exactly what it is, so I'm going to leave it in that form of natural log of 4. If you want, you could change it to 2 multiplied by the natural log of 2 and see what you got. So YG was mentioning 2 squared because he's looking at the 4 and thinking I could use a power rule. Totally fine as well. So if you had it written as 2 natural log of 2, that would be fine too. So, but yeah, I see natural log of 4 in the exact same way as I see 1, and I see it different to things like this. I see these as functions or variables or something that depends on an x. The other two, the yellow highlighter, those just look to me like numbers. So even though that natural log is there and you're thinking natural log is this type of a function kind of thing, natural log, sure, when it's natural log of x or x plus 1 or something, you think of it like a function. But natural log of 4 is just a number, as is log to the base 10 of 4, whatever it might be. So leave it in that form. But if as an understanding kind of thing, think of it like a number. Okay. Any questions there? Okay, something else to be aware of. Go ahead, Jamal. If you try to be more specific, try to write down or unmute and say exactly what you don't get about it, and then I can address that. So just while Jamal is going to figure out how to ask the question, I am going to move on a little bit to the change of base formula. Do you want to unmute, Jamal? Might be easier than typing. The entire question, I have a hard time getting this topic. Okay, so let me just spin over the question one more time here. This topic was about expanding logarithms. So it was about taking log of a very, very complicated function and trying to apply all of our log laws as much as possible to get it to be a sum of a whole bunch of easy log functions. And we're going to do that using the log laws. It starts with noticing that the main kind of thing that you see inside this log that makes it complicated, the very first thing, is like a log of a over b, where this top part here, I'm looking at that as an a, and this bottom part here that I've highlighted, I'm looking at that as a b. The log law that we have for that, you can see it written there in blue, and we're just going to apply that directly to it and separate it out to get to here. Now we have one really complicated log function that we started off with, the one at the top, written as two, still kind of complicated, but definitely less complicated looking log functions just below. We have another log law that can help you deal with when you have a product inside logs. You can see the log law written here. And the rule that you apply is that you can, when they're multiplying inside the log, you can separate them out. It's log of this thing plus log of that thing plus log of that thing, which we've done. We had the 4, log of 4, e to the 2x, and x plus 1. They get separated out that way by that log law number 5, I think it was in the notes. Same thing happened to the second log term, and we apply that to the second log term in the very same way. Now it's looking a lot easier. Right now there's 5 log terms in there, but they're all looking much easier. They're all not looking quite as complicated. You don't have things multiplying and dividing all inside in there. But the last thing that we do to make this a bit simpler is use the power law, which says that you can bring it down. The power law there you can see written in the center of the screen in the blue. If you have a power over something inside the log, you can bring the power outside the log. That was one of our rules as well. So we apply that and then take away all the powers from those log terms. And now it started off as something very big and complicated in the very top of the screen. And now it is something a lot more simple. Natural log of 4 plus 2x natural log of e and so on. And we finally had this thing of natural log of e was 1 because it's log to the base e of e. When the base and the thing inside are the same, the answer is going to be 1. Another log law we had. After this, it was just some addition of that. And just at the very end, all we were talking about was what actually is natural log of 4? It's just a number. When you see that, if I say, what is that roughly? What is it? What I'm hoping that comes to most of your minds will be, I'm thinking you should go, what is that? If I try to evaluate that, my base is e. In order to kind of evaluate the size of that term or that number, I have to go, what power would I have to put on the e so that e to the power of what makes 4? E is about 2.7, so if I want to know how big that is, 2.7 to the power of what would make 4? I'm guessing it would be something like 1.3 or 2 maybe. You could probably use a calculator to find out, but we're not using calculators for this course. It doesn't really matter to me. It's more about the mechanics of the log laws that I care about here. So, but it's also just something that I want you to have an understanding of like, what am I looking at when I see natural log of 4? And I see natural log of 4 as in the same category as 2 or 5 or 7 or pi. It's a number. I see it different to the x, the natural log of x plus 1, and the natural log of x minus 3. So it's kind of what category was all I was talking about there. Okay. If you have any further questions about it, do send an email. Okay. I do have to move on though. I have to get through more log stuff and get through a good chunk of trig today. So, but yeah, no worries. Just send an email if you're not sure. It's always better if you can be specific as well. So if you can work through it yourself and think, here is where I don't get it, that's always much easier to help with. Oh yeah, the change of base formula. So let's say we have a, b, and r greater than 0. A and b are not equal to 1. Then we have this formula. Log to the base a of r is equal to log to the base b of r divided by log to the base b of a. So this is a formula that I'm sure you've seen in school a whole lot. And again, it seems like this weird kind of mysterious thing where we have we have 3 different kind of variables a, b, and r in here. Maybe you're using different letters in school. You might use x, y, and z. It doesn't really matter which letters you use. So you kind of see this formula just boxed off in a textbook and maybe highlighted and said, this is the change of base formula. And you're like, okay, what does that mean? this is a formula that allows you to express a log any given base. Sorry, a log with any given base. You're allowed to express it in a log with any base you choose, any different base. So for example, let's just go through with a couple of numbers first, right? Let's say you say to me, you know, I have this thing I'm working with, log to the base 2 of x, it's in this question. If I want, I can change this to be a log expression, not having base 2, having base 3, having base 4, having base 5, having base 10, having base e for all I want. It can be any base you choose. So this is the same as log to the base 3 of x divided by log to the base 3 of 2. It can be log to the base 4 of x divided by log to the base 4 of 2. It can be natural log of x divided by natural log of 2, whatever you want it to be. So some of the notes about this formula is you can choose what the b is. That's something to note. And I'd like to say, oh, you make it whatever you want. You know, it's kind of this way that you can say b can be anything, it's up to you. The question might dictate that it's better for you to choose b to be some particular number instead of just anything at all, and that's something you might have to figure out. But the idea is that b is the thing that you decide what you want it to be. And the a part, that's what's going to be given to you in the question, or what you're working with to begin with. And b is going to be how you change it to fit your needs. Now the r is just the thing that's inside the log as well. That's what's given. And you'll notice that this here on the bottom line, this 2, that's always going to match the original base. Okay? So in the new fraction that you make, the base in the log is always going to be what you choose it to be. In one context, you might want it to be a 3. In one, you might want it to be 4. In another one, you might want it to be just natural log. And what's up top, that's going to match what you started with. Okay? So I think the main thing to remember here is that what b is open. It's up to you. It's not like some formulas where you apply the formula and that side equals that side and that's the rule. The b is open and it's up to you to decide. Okay. Are there any questions so far about this change of base formula? So I mentioned that we're not using calculators in this course. It might be a good exercise for you to use a calculator and just verify this for yourself with a bunch of questions. So maybe just as a exercise to satisfy your kind of understanding of this, use a calculator to verify that, for example, log to the base, let's say 3 of 5, right? That's equal to log to the base 2 of 5 over log to the base 2 of 3. It's equal to log to the base 7 of 5 divided by log to the base 7 of 3. It's equal to the natural log of 5 over the natural log of 3. So what I'm saying to you is to do this on the calculator, and if you do that on the calculator, that on the calculator, that on the calculator, you should get the same answer for every single one of them. And actually, I'm going to go through it here now, since we're talking about it. So I don't know what your calculators look like. We probably all have different ones, but if you see that button on the top right, I hope that my screen is not mirrored, because that looks like a mirror vision to me as I'm looking at it. But you're going to hit that one there. So what I'm going to do is log to the base 3 of 5, and I get 1.464, blah, blah, blah. That was log to the base 3 of 5. This was the 1.46497. So let's just pick this one. It doesn't matter which one we do, right? That one should also be 1.46497. So let's see what we do. Log to the base 7 of 5 divided by, where are we going? Log to the base 7 of 3. So you can see it in my calculator screen. I've typed in exactly what is, I hope that you can see my little window here. I'm holding the calculator really close to it, so I'm hoping that you can see the calculator. But I've typed in exactly log to the base 7 of 5 divided by log to the base 7 of 3. And when you do the calculation, you get the same thing that you started with. That works for any base. So what I'm just going to do is go back and do the second one as well. I give you an exercise and then I do it anyway. You can't see the calculator. Really? So you don't see me in some little window? Can anybody else see me? Oh, some can, some can't. Not clear. Okay. You're gonna have to trust me, or maybe just do it on your own calculator. It's probably good. Some of you can and some of you can't. So yeah. Oh, Jasmine just left the meeting, so I guess she was having trouble anyway. For those that can, it's probably a little bit blurrier in a small window, but you get the idea. Here I've just replaced the base of 7 with the base of 2, and the same answer comes out. So that's the change of base formula. You can, given like a log to the base 3 of 5, you can make a new base, any one you want. I chose some examples of 2, 7, and base e. And each time you do it, you're going to get 1.46497, 1.46497. And if you do it with the natural log as well, you're going to get the same thing as well. So yeah, that's really all I'm banging on about here. Now, you might be wondering why you might use this. Honestly, for a lot of logs that you see, you might be kind of wondering why I'm going to use it. For something interesting that I unfortunately don't have time to discuss, if you look at how logarithms were used in the 60s and 70s before everybody had like a high-powered computer in their pocket and calculators everywhere, you might find some interesting things. But there's the movie, what's it called? Hidden Figures, where there was calculations being done about sending a rocket into space, and numbers are there's going to be very, very big numbers, and people have to multiply numbers very big. Logs and log tables were a technique that were used to multiply very, very large numbers that you normally can't do in your head. It was about changing them into logs. You're then adding small numbers based on what used to be, based on what was a multiplication of big numbers. It now becomes an addition of big numbers. So it was like this. If you have two massive numbers, A and B, to multiply, right? And you say, oh, I don't know what that is. However, what I can do is, I know this rule that we just went through. That's log of A plus log of B. You had these big tables that you would look up. You go to page whatever for the logs that have base 10. You go to page whatever for base 10. You would look up your numbers A and B, and you would find those numbers are usually relatively small. You can do the addition easily enough because addition is not as tough as multiplication. And I guess the people who had these jobs were very, very good at adding numbers with bunches of decimals and things. That's much easier to do. So you can say, oh, that when I add this, I get 15.24389. Well, so now I have that log of AB is equal to 15.24389. That means that AB is equal to, where are we going here? 10 to the power of 15.24. No, oh no, sorry. You have to reverse and go back to your log tables. So once you have this number here, you find that in the table, in the log table that you have, and then you kind of reverse engineer what you did in the beginning to figure out what AB must be in the log tables. Okay, this would take an hour to explain probably, and I'm trying to do it in 2 minutes, and also forgetting because I haven't thought about it in years. But it was useful to use logs like this as a way to multiply very, very large numbers. You could transform it into an addition of small numbers and then reverse the technique and go back to say, okay, well, that means that the product of the two big numbers must have been this. I wonder if I could maybe try and find something online for you to look at, a video or a document explaining it, because it is really interesting. We still have logs and they're still useful, but we also have supercomputers in our pocket pretty much. Compared to what they had back then, it's not a supercomputer, but compared to what they had back then, it's pretty super. And a lot of this stuff is lost because we can just multiply numbers in 2 seconds on our phone. So we don't really need all these techniques. But a lot of the math that goes on now using logs, that's all still necessary, and understanding of logs is still necessary in order to do certain things. But here we are still talking about the basic rules that you kind of started with. So let me get back on track here. I'm going on a lot of tangents today. Okay. So this is the change of base formula. Okay, so let's just run through an example where kind of selecting a base and running through some mechanics is going to be necessary here. So this time I'm actually going in the opposite direction to what we did originally, and it's write log to the base 2 of x plus 1 plus log to the base 8 of x minus 1 as a single log expression. So this time we are going to make it into something more complicated, but we're going to go backwards. We're actually going to use the log laws kind of in reverse. It's sort of like the opposite of expand this log expression to compress it or something, or write it as a single log expression in that way. It's not something that you're going to find yourself wanting to do, but I'm going to do it in this one just because it's going to incorporate use of the change of base formula here. Okay, so what I hope a lot of you are thinking about right now is that I have this rule. If I just use it backwards, log of A plus log of B is equal to log of AB. I'm hoping that you're looking at this plus sign here and thinking, well, I have a log law that should help me write that as a single log expression. But I have a problem. When this has to be, in order to use this has to be the same base. So in order to use pretty much any of the log laws, but just for this case, the above log law, we need the logs to have the same base, okay? But we don't here. We don't have them having the same base. We have a log to the base 2 and a log to the base 8. So conveniently enough, we have a formula, if we scroll up, that allows us to change the base of a log function. So the approach that we're going to take is we're going to pick either 2 or the 8 and change either the 2 to the 8 or change the 8 to the 2. So let me just go back to rewriting the question here. We had log to the base 2 of x plus 1 plus log to the base 8 of x minus 1. The problem is the different bases. So let's make every log term that we see here have the same base. Let's change that 8 to a 2 by using the formula. So remember, when we're going from here to here, this here is the new base that you want. What's in the numerator, the x minus 1, that has to match. If you look at the green highlighter in the example there, the new base that you select in the numerator, that's going to be, the argument is going to be the same. It was x in the example there, but we had x minus 1 in the one that I just did. And the one in the denominator, the 2 that you see here in this example in the denominator, that is the old base. And the old base in this one, it was also 2. Or sorry, the old base was 8. The old base was 8. The new base is 2. Okay? So this looks like progress because all of our logs have the same base. So now at least some of those log laws that we know can actually be applied. I just noticed the chat again. Jasmine, I noticed you left and came back, probably trying to fix the camera or something. I would say just skip to this part of, I'm going to post a recording, so if you, hopefully the camera is clear enough on the recording, and you can kind of rewatch this and see that the numbers all match. And also for anybody else who had trouble seeing it maybe live, hopefully the recording is clear and you can see the numbers in the recording if you wanted to review this. Where are we going? Okay, so it's a good thing. We now have them all to have the same base, but this looks tricky. We don't have a log law, and this is why I really had this question in here. We do have a log law for this. Not ln of a over ln of b equals, right? There is no log law for that. But unfortunately, that is what we see here. We have a log of a over a log of b. So that log law won't apply. We do have a log law for addition, the one that I wrote up here. But how does that work if it's like over something else? What do you do here? So it looks a little tricky right now. I'm just going to take away this stuff that I've is now in the way. Any ideas what we can do? Anybody offer a suggestion? Maybe it's a little tough. I will keep going because I can only pause for so long. But if you have an idea of what it is, please put it into the chat. What's troubling me here is the denominator, log to the base 2 of 8. That's kind of in the way of everything in the previous expanding question. We'll get there, Evan, but we're just not there yet. The log to the base 2 of 8 in the denominator, this one here, that's kind of getting in the way. Like we have log of a plus log of b equals log of ab. But what is it when it's log of a plus log of b over log of c or something, right? What then? Where does that fit in? So that's kind of where we're at right now. We can't really use the law because it's not really in the right form just now. And that thing in the denominator, that log to the base 2 of x or log to the base 2 of 8 is a problem. But what I'm thinking though is that what is log to the base 2 of 8? This is something somebody should have put in the chat. What is the answer to log to the base 2 of 8 if this is just a question on its own? Okay, what comes into your mind when I say log to the base 2 of 8? Thank you, Ayush. 3. That can be simplified a lot. It's just 3. So this is log to the base 2 of x plus 1 plus log to the base 2 of x minus 1 over 3. Now, that still looks tough. When we have log to the base a in our law that we're talking about, it's always just log to the base a, or sorry, log of a plus log of b. It's never log of a plus log of b over 3 or over 4. But we still can do something here. And maybe just to help people along in figuring out what it's going to be, dividing by 3 is the same as multiplying by 1/3. We agree with that? Dividing by 2 is the same as multiplying something by 1/2. And I like multiplication more here as a visual than division. Because what can I do to make this a little nicer to apply that log law? Well, we have a very convenient rule that looks a little like this. This is the way you would have learned it. But that can also work in reverse. if the p can go down, it can also go up again. So what we want to do is move that power up. Now we can apply the log law. Now we can say, oh, well, this is that, and we're finished. It's now written as a single log expression. So a little bit of gymnastics there we have to do. We have to kind of use the change of base formula to get all the same base. We have to say, oh, wait, but log to the base 2 of 8 is 3. Well, dividing by 3, that's the exact same thing as multiplying by 1/3. So let's think of it as multiplication, because we have a log law that if we have a number multiplying by a log expression like that, we can move that number multiplying up to be a power. And now we can apply the log law. So this would be a probably the most challenging example you're going to see in the log section of this course. Something that belongs in an assignment, but not in a final exam, if you know what I mean. This is the kind of thing you have time to figure out, to look up your books and things and sort of research it a little bit and say, this is what I have to do. But not something I'd ask in a short time situation. So I would say expect something like this in your assignment, but not in your final. Can log to the base 8? Yes, it could. You could do it that way as well. And actually, that's a really good exercise. Wait a second. Sorry, I thought you were asking something different for a second. Oh, wait, log to the base 2. That wouldn't be the way that I would... Sorry, as soon as I read your question, I thought that you were suggesting, at the very beginning of this, we decided to take the 8 and write it as a 2 instead. I was wondering if you were asking, could you write the 2 as an 8 instead, which you can do, and now that I've thought of it, it's probably a good exercise to try and do it too. 1/3. I'm not certain. Let me just write something there for a second, Eric. So you're saying, I'm just going to write this in a different color because it's not really part of what we're doing here. So log to the base 8 of x minus 1, 2 cubed. Yeah, I guess you could use the change of base formula now. So the issue is that you want that base and that base to be the same. So changing it straight away, changing 8 to 2 cubed, it still doesn't make it the same base because it's 2 cubed and not 2. So, but I could apply the change of base formula now and call it, let's say I want my new base of 2. And here's log to the base 2 of 2 cubed. Yeah, it works. So you can call it log to the base 2 of x minus 1. Log to the base 2 of 2 to the power of 3 is just equal to 3. So it would be the same thing, I think. And then you would have the 1/3. The base 2 of x minus 1. Yeah, that would be good too. Yeah, very good. You're not really dodging the change of base formula at all. It's still in there. But yeah, it's going to be the same approach. Yeah. I never really thought of doing it before. I never really thought of putting a base as having an exponent in it. But yeah. Okay, so there should be an example or two in the notes of doing that. So definitely make sure that you practice those ones. And a couple of other topics in logs here. So using logs to solve exponential equations is going to be the first one. And then we're just going to solve actual log equations afterwards, and then we're going to be done with log. So we'll probably take a break after we've covered those two sections. But I think you're going to find this a little more straightforward than the last one. So let's say examples. Let's say we have to solve 3 to the power of x equals 5. Okay. We did exponential equations last week, and it looked kind of like this. We might say 3 to the power of x, let's say it was equal to 27. And we would have to say, oh, well, 27 is 3 cubed, and then we have this rule that kind of says x equals 3, right? That was the main way that we had to solve exponential equations. But here we have a problem, that this kind of thing isn't really going to work here, because 3 to the x equals 5. I can't take that 5 and rewrite it as 3 squared or 3 to the power 1 or 3 to the power 3. It's a number that doesn't just naturally have 3 as a base. You can't rewrite it with 3 as a base like that. So how do I get to that x? Well, here's what we do. Logs help, because as we're looking at that equation, we're thinking, okay, 5 can't be manipulated to be 3 to the power 1 or 3 to the power 2. Eyeballing this and kind of thinking, what would roughly be the answer? I'm probably going to guess about 1.1 or 1.2, because it's got to be a number between 1 and 2. And I'm not a human calculator, and I can't figure out exactly what it is. But it's nice to have an idea of what it is roughly. Probably somewhere between 1.1 and 1.2. I don't know, actually. I'll do it on the calculator afterwards and just see what it is in the end. So when I'm looking at that, next thing I'm thinking about now is, since I can't do anything with the 5 to make this easier, I want that x out of the exponent, out of the power, and down onto the sort of numerator line, so that I can say x equals something. Now, how am I going to do that? Well, luckily, I know of a function that allows me to move powers down in front, and that is the log function. So I can say, okay, I have 3 to the power of x equals 5. What I can do is take the natural log of both sides. Actually, I can take log to any base of both sides. It doesn't matter. Any base I want. But I'm going to use natural log because you're going to see it a lot in future maths that you do. It tends to be a favorite of university instructors. And but any log you want would work. I'm going to use this rule that allows me to bring the x down. And then divide across. This is almost another verification of the change of base formula, because let's say you had used log to the base 2. Then you would be seeing log to the base 2 of 5 divided by log to the base 2 of 3. So you can see in that format the base doesn't matter and the answer is the same. That's what you saw in the change of base formula as well, so it kind of supports that. So natural log of 5 divided by natural log of 3. And what was I guessing? That maybe it was like 1.1 or 1.2 or something like that. I have no idea if that's correct. Let's see what it was. Natural log of 5 divided by natural log of 2. So I don't know if you can see this here, but that's what we have on the screen. 2. Oh, I had it totally wrong. Oh, I've written it wrong. It was natural log of 3 was what was in the question. So sorry, I should have had natural log of 3 in the denominator. That's what was in the question. And it's a little bit blurry. I can see it's not focusing. Oh, 1.4. So I was a bit off. But it's nice to have some sort of a ballpark figure of what you would expect the answer to be. You don't want to be totally blind and not understanding logs and things. You want to roughly know what's going on in here. Okay, so let's do a slightly harder one, but it's going to be the same thing again. I think this is something you can definitely spend some time practicing, and it shouldn't be too hard. 5 to the power of 2x plus 1 equals 7 to the power of x plus 3. Again, before we knew what logs were and knew about that special rule of logarithms, we would have to try and make 5 and 7 have the same base somehow. That's not really going to happen unless you're a human calculator and can just do it in your head. And if I saw somebody doing it in a test, I would say, haha, look, they use a calculator, 0 marks. So I'm going to want to see evidence that you're using it the way I'm showing you. We'd like to get those x's down out of the denominators. So we're going to take the natural log of both sides. Bring down those powers. Don't forget your brackets here. The entire power is going to be multiplying. And now the question is to solve for x. And it's something that I hope most of you will be very comfortable doing now. We're going to multiply out brackets. 1 times natural log of 5 would just be natural log of 5. Next thing you should be thinking is we get all the terms with x on the left side of the equation, all the terms without x on the other side. So 2x times natural log of 5 minus x times natural log of 7 is equal to 3 times natural log of 7 minus natural log of 5. What always comes next in a kind of solve for x question like this is to factor out the x. Again, common term factoring is a skill that you definitely don't want any trouble with. This is why I went back to kind of pre-high school stuff almost to go over common term factoring again. And how do you isolate the x? Well, you divide across by whatever x is multiplying by. Because that will cancel with that and give us the answer. X is equal to 3 times natural log of 7 minus natural log of 5 divided by 2 times natural log of 5 minus natural log of 7. Slow down, okay, no problem. So I think we can see everything on the screen there. A quick recap then. We're trying to solve 5 to the power of 2x plus 1 equals 7 to the power of x plus 3. So what value of x can make those equal? Now, whenever we're trying to solve for x, what we want is something that looks like this, like x equals something. It might be complicated, it might be simple, who knows, we're going to find out. But we want x down as a regular term, like in a numerator, not stuck up in the power of a number like 5 or 7, okay? So what is the convenient function type that can allow us to move powers down to the regular position? It's logs. So what we're going to do is take the log of both sides. So we took the log of both sides in, I'm just going to start writing on the screen here so we can indicate where I am. Taking the log of both sides in the first step here. I want to do that because that allows me to bring powers down in front to be multiplication instead. That's all you see in the next step. 2x plus 1 was the power, it comes down in front. X plus 3 was the power, it came down in front. And after that, we're now just trying to isolate to get x on its own down here. So what do we have to do? If you see x is tied up inside of brackets, well, you'd better multiply out the brackets. 2x times natural log of 5 plus 1 times natural log of 5, that's what you see here. X times natural log of 7 plus 3 times natural log of 7, that's what you see here. Yes, but the only log law was the very, very first one. The one that you see up here where we took the power down. That was the only log law. The rest was like, yeah, honestly, it almost completely parallels this. So what did we have here? We had 2x plus 1. Let's say you have 2x plus 1 times y equals x plus 3 times z. And the question is to isolate x. So we're going to say, well, that's going to be 2xy plus y. That's xz plus 3z. I want the x's on one side and I want the y's on the other, and so on. Except in this case that we just did, y was log, what was y again? Y was natural log of 5. And z was natural log of 7. So it looks nasty. You have all these log things in among all the question. But this is like your y and that's like your z. So you have 2xy minus plus y, you have xz plus 3 times z, and so on. And you're just multiplying out brackets, bringing things across to equal signs, factoring and dividing. It's all the stuff you would do, I hope, if you were solving this thing here for x, this one here. Okay. So it looks a bit uglier, it looks a bit more clunky and unfamiliar because there's logs in there. But it's the same thing really. Okay, so where were we? Yeah, we brought the x. We had an x over on this side here, so we brought it across the equal sign. We had something that didn't have the x, so we brought it over here. The sign changed. We found an x here and an x here and said, okay, we should use common term factoring and factor that out. So when you factor the x out, you're left with 2 log 5, which is here. You're left with just negative log 7, which is here. And then you're going to divide across by that factor. Okay. So that's something that you're going to have to do a bit of practice on. Again, there's a ton of examples in the book. I think that you know all the mechanics. The only thing that's different that happened here that might be something that you wouldn't be 100% comfortable with is that there was a choosing to take the log of both sides in the beginning and applying a log law in the beginning as well. Everything that came after that, I think, should be just, if you're practicing enough, it should feel a lot like muscle memory, that you're just going to like bring the x across, I factor out, I divide. But there's probably just a general sense of uneasiness or unfamiliarity because it looks different to equations you've done. So definitely just spend some time practicing and making sure that you can do it with the questions that I made for you in the book, and check with the answers in the book and everything. And the last topic then that we're going to look at in logs is about solving logarithmic equations. So our examples here are, first of all, log to the base. No, I'm not using the base 3, sorry. I was just doing log of x minus 3 plus log of x equal to 1. So again, when you say solve this thing for x, is kind of the invisible instruction, we're hoping to get x equals this thing as the answer. Now, this time the difficulty is that the x's that you're trying to isolate, they're stuck inside these log functions, and we need to get them out of the log function somehow. So the log laws are going to do that for us. Now, there's often a few ways to go about this, but this is another case where turning multiple log expressions into a single log expression is helpful, because what we can do is then change that single log equation that you're going to have it in the end. You're going to turn that into exponential form, and that's going to release the thing from inside the log brackets to being outside and therefore solvable. So what I'm seeing here is, first of all, that I have a log law that I can apply. This time the bases are the same, so I can apply this log law, and just multiplying out, what I'm seeing is x squared minus 3x inside in here is equal to 1. Now, okay, whenever you see a log of a thing like that without the base being specified, don't forget that the invisible base that's actually there is base 10. So what I'm going to do is use that that equivalence that you have between a logarithmic equation to change it to an exponential equation. That's going to free the x squared minus 3x, and hopefully be able to work with everything else that's there. So if you remember how to rewrite, we did this last week, how to rewrite log equations as exponential equations. This is equivalent to saying that 10, which is the base, to the power on the other side of the equal sign, that's equal to what's inside the log expression. Remember this? It's a slightly more complicated version of log to the base 2 of 8 being equal to 3, being equivalent to 2 cubed equals 8. That we were practicing with smaller ones like that last week to get used to the switchover. Now we have slightly more complicated things with variables involved, but it's the same process as last time. Base to the power of thing on the other side of the equal sign equals thing inside brackets. So that's what we're doing here. And now we have an equation that we can solve. There is a twist coming. So it's something that we're going to have to navigate. When we factor this one, it's x minus 5 by x plus 2. I think, yep. So x equals 5 and x equals negative 2. Now this is something that I'm not really expecting most of you to catch, but it can happen when you're solving logarithmic equations. Sometimes a false solution comes along when you're solving logarithmic equations. Does anybody know what the false solution is here? I'm going to give you a minute or two to look at this and maybe try to figure out either the 5 or the negative 2. Well done, Jamal. You're correct. So it is the negative 2. Why is the negative 2 false? You might find it handier to unmute here rather than trying to type. Go ahead, Jamal. Unmute there and tell me why you think negative 2 doesn't work. Okay. See, this is why I want you to unmute. That's what you've rolled is technically incorrect, but I know that you have the right idea. Try to phrase it into something that's technically correct, not just kind of with the sort of saying the word negative and hoping, you know what I mean? Logs can be negative. If you take log to the base 2 of 0.5 or something, you're going to get a negative answer. Again, the phrasing is off. The phrasing is a little off, Lewis. So I'm being a bit of a stickler here. I think that you have the right idea. I'm not trying to shoot you down and say you're wrong or something, because I'm pretty sure that you have the right idea of why negative 2 doesn't work. Yes, Stephen, that's more along the lines. The component of the log can't be negative. But really, I think the word that everyone's looking for is the argument. That's just a more technical word for it. But yes, and what it is that you can't take the log of a negative number. So I'm just going to write this down for everybody. You can't take log of negative number. But it's not that logs can't be negative. You can't take the log of a negative number. And these little subtleties of language are much more important than math. Well, they're probably important in every subject, every university subject, but they're crucial in maths. You have to be saying the right thing exactly, or you're saying the wrong thing. That's math. So, for example, if I try to do the natural log of minus 5 in here in my calculator, I hope this clears up a little bit. It's going to give me an error, right? I can't do it. So, component of log cannot be negative. I can't do log of minus 5, for example. But can the answer of a log be negative, or can a log be negative? let's say I do natural log of 0.5 minus something, right? So you can get a negative answer from a log, but you can't take the log of a negative number. I know I sound like I'm being extremely fussy right now, and this is important in maths. You know what? Even as we're talking about it now, I want to make sure everybody's paying attention to this and thinking about it. I'm thinking about what's going to go on your quiz on Friday. I'm strongly considering putting a multi-select answer right now, where I'm going to have a bunch of sentences like this, where the words are a bit messed up. Logs can be negative. Logs can't be negative. You can't take log of a negative number. Maybe select the right one. That's really what I'm beginning to think of, because it is important. It's going to be tricky and all, but I want you to think about this and to be sure that you're that you definitely understand it. So this one here doesn't work because, as a couple of you mentioned, you can't take log of a negative number. Now, what would happen if I plug -2 into the original question in here? I would have log of -5 and log of -2. That's a problem. So whenever you solve a log question like this, you have to go back and say, okay, of the solutions I have, are any of them going to cause a problem? One of them does in this case, so you throw it away. Now you might be wondering, why the hell did that happen? Like, I followed all the steps, I followed the rules and everything. Okay, let's say we have log of AB here, right? If A and B, if they're both negative, then A times B is positive. So log of AB works, but log of A plus log of B does not work, because you can't take log of negative number, as we found out. And even as you, if you remember, negative numbers aren't in the domain. The graph of log looks like that. This here doesn't work. You can't take log of negative number out there. So we probably have to rewind all the way back to last week and look at, and to the textbook, and look at how the rules are set up. But you'll notice that at the top of the thing, before I gave you all those log laws, some of them are that A, this is not 1, this is not 0, this is greater than 0. Greater than 0 is the key. Those log laws only apply for A's and B's that are greater than 0. So the log law, what we'd have to do is say something like, provided A and B are greater than 0, then we can use this log law and so on. But the easiest way to navigate it is to just, work your way through the problem, apply the log law, solve the question, and then check your answers in the end. So what I'll just say here is, don't forget to check answer after finishing a log equation question. Okay. Can't take the log of a negative number. Let's do another example. I'm going to take a short break after that. Move on to trigonometry then. So let's say we have to solve natural log of x plus 2 minus the natural log of 2x plus 1 equals natural log of x. So there's a couple of options here. What we could do is just simplify the left side, and since they have the same base, you can say if we have log of A equals log of B, then A equals B. Or we could bring the log x across to the left side, simplify it all into 1, and work it that way. So both of those are options to solve this problem. What if we do get a negative answer? Do we leave that, or do we? No, you won't include -2. So I would want to see something like what I've written here. You get those two things out, and you're going to indicate to me somehow that x equals -2 does not work because you can't take log of a negative number. So x equals 5 is the only solution. So let me just, 5 is the only solution. Yeah, you have to. So if this was an assignment that I'm marking, and you came down and you just got x equals 5 and x equals -2 and stopped, I would say you're not finished, because one of those doesn't work and you want to be communicating why not. So you're probably getting 3.5 or 4 out of 5 or something, depending on whatever way I'm doing it. Yeah, it's an important feature of those questions. Okay, so the last time we saw this, I think what we did was we had all the log terms on one side and then we changed it to exponents. I'm going to do a little different this time, and we're going to have log A equals log B, and then say, oh, we can cancel the logs then as part of that. I think the very last log law that we covered, I think it was, where you can kind of drop the logs because they're at the same base. So let's do it that way. Log of x plus 2 minus log of 2x plus 1 equals log of x. So this time I'm seeing the minus sign. So I know that it's going to be a division on this side. X plus 2 divided by 2x plus 1 equals natural log of x. So we have the same base on both sides. The base is e. So we can say then that x plus 2 divided by 2x plus 1 is equal to x. Now, again, I'm just going to point out that we might get a false solution. We may or we may not. We'll have to see in the end. But if there is some value of x that works in here, we might end up finding that negative divided by negative can be positive. So that might be defined, the one that I've just put on the green highlighter. But they might make these two things negative. So it won't be a solution to the original question. So again, just be ready to watch out for false solutions like that. But it's something that we can worry about at the end. If I was being a real stickler, every time you apply a log law, I would be mentioning, you would have to say something like, provided x plus 2 and 2x plus 1 are greater than 0. Kind of introducing it at this point and then saying only solutions that follow, they all have to satisfy that condition. I'm fine with you if you just revisit it in the end and check. So I'm being a bit more lenient than a more kind of strict university instructor might be here, but I think it's okay. Where are we going? Okay, so we're going to solve for x here now. And again, I hope that this part is probably straightforward enough for most of you. We're going to just multiply across, expand some brackets. So I'm seeing an x that will cancel on both sides here. So 2x squared is equal to 2. X squared should be equal to 1. So that means that x is equal to 1 and x is equal to negative 1. Now, again, when we go back here, I'm just going to say here, checking answers. So if I check x equals 1 in here, natural log of 1 plus 3 minus natural log of 2 times 1 plus 1 is equal to natural log of 1. That looks okay to me. I'm not seeing anything negative inside the logs in here. Natural log of minus 1 plus 3 minus natural log of 2 times minus 1 plus 1 is equal to natural log of minus 1. I'm seeing a problem here because this and this, these are not defined. So x equals 1 is a false solution. Sorry, x equals negative 1 is a false solution. So the only solution is x equals 1. So I'll probably just go back up here, maybe get a red pen and say, that one doesn't work. So yeah, that would be a more well-presented answer, Evan. You're checking your answers and you're demonstrating to me why one of them doesn't work. Okay. Are there any questions right now? You know what, if you're not sure about something, you can figure out over the next, whatever it is, until 11:35, 13 minutes, and write in the chat. But for right now, I'm going to say break until 11:35. Okay, so we'll take a break here. Go get a snack or a drink of water or something, and we'll resume after that. We're starting on trigonometry. Okay, we'll be getting started now on trigonometry. Honestly, I would say that you'll find the rest of this class pretty easy, because I'm going to pretty much, whoops, what has happened? My screen's all went off for a second. One of them now isn't working. Now it's working. Okay. I think that you're going to find the rest of the class comfortable enough, because I'm pretty much redoing trigonometry from scratch. I'm going to run through it pretty quickly, obviously, but we won't really be getting to the hard stuff until next class. So I need to stop presenting here. And present over here. Okay, so I'm going to run through some terminology first, and once it gets a little bit more complicated, I'm going to switch back to the screen to write on from then on. Starting with some terminology. An angle is formed when a ray is rotated about its endpoint. So, and in the context of trigonometry, we're always going to be kind of with our XY axis here, and not just have angles kind of anywhere on the whole thing. In this case, the initial side is going to be the x-axis. The standard position of the angle is to start in at the origin in here, and the ray that we talked about in the previous one, that is the line that goes straight out from the origin. We measure the angle as counterclockwise from its initial side, and whatever size the angle is, that is the angle that we're going to be talking about for trigonometry. If an angle is formed positively, we're going to consider that, positive angles are those from which the ray was rotated counterclockwise. Clockwise is negative in this case. You might remember some terminology. Acute angles are angles between 0 and 90 degrees. A right angle is an angle of exactly 90 degrees. An obtuse angle is between 90 and 180. A straight angle is exactly 180 degrees. One I'm not seeing on my little list here is a reflex angle. Some of you might have heard of reflex angles. Those are when the angle is bigger than 180. Complementary angles are two angles that add up to make 90 degrees. So for example, 70 and 20 degrees. 20 is the complement of 70 and 70 is the complement of 20. Supplementary angles are angles that add to make 180 degrees. For example, 120 and 60 are supplementary angles, and in the same way, the supplement of 60 is 120, and the supplement of 120 is 60. And that's pretty much where we stop talking about angles, because in university, 99.99% of the time, your professors are going to talk about radians and not degrees. So we're not really going to be talking about angles in the sense of degrees. It'll all be about radians from now on, except for a few little cases I might go back to degrees. So what is a radian? Well, a radian is approximately 57.3 degrees, but it's the size of the angle you get, where if you start with this initial side and keep rotating so that this initial side that you started with, the length of that is equal to the length of the arc that's traced out. Once you've done that, then you've gone 1 radian. So a radian is the size of the angle that causes R to be equal to S here in length. And radians normally aren't talked about in terms of 1 radians, 2 radians, and so on. We usually talk about pi multiples of radians, whether pi fractions of them, pi over 3 radians, 2 pi radians, pi radians, pi over 6 radians, things like this. Yeah, so changing from degrees to radians, your rule is that you multiply by pi over 180. To change from radians back to degrees again, you multiply by 180 over pi. This is another example of how pi is a special number, because this radian is made by making the initial side equal to the arc length, and it's the angle that does that size. But pi again is just like how I went on at length about how special E was for all the places it shows up in the world. Pi also shows up a lot in scientific scenarios, calculations, and things. In the first place, it was really being noticed was in circles. It's that 2 pi radians is gives you the full circle. Pi radians gives you 180 degrees. So it's a very important number, coming up in lots of places. But I guess that's why we're always talking about pi multiples of radians, because pi is this special number, especially in circles. So a few examples here. There's nothing really much to do yet. We're just going to play with converting from degrees to radians and backwards and forwards again. So 60 degrees, if you want to convert it to radians, if you remember, you're going to multiply by pi over 180, and 60 degrees is equal to pi over 3 radians. If you want to convert radians to degrees, you're going to take your radians, for example, pi over 4 radians. To convert that to degrees, you multiply by 180 over pi, and you get 45 degrees. So just a quick example to show, if you see an angle measured in one unit type, how you can quickly get to the other unit type depending on your needs. It's awkward. I know we'd all rather talk about degrees, because I think we all have a sense for roughly how many degrees, how big a certain amount of degrees are. Like if I said to you about 60 degrees, I'm sure you'd be going about, thereabouts kind of, and you'd be able to sort of say roughly how big that angle is. We haven't really got the same intuition with radians, but it's something that you kind of learn over time, the more you use them. So it's also something that we'll have to get through to think about. Oh yeah, there was complement and supplement. So you can also find the complement of an angle and the supplement of an angle. The complement of pi over 3 is the angle that you add to pi over 3 to get 90 degrees, or pi over 2 radians, whichever unit you're talking about. So first of all, convert the 90 degrees to radians, and you get pi over 2 radians. After a while, you just begin to know what all the the important angles are. And so solve it. So you want to solve for the angle theta such that pi over 3 plus this theta is equal to pi over 2. Well, you're just going to bring the pi over 3 across, get the common denominator, and add them up, and you get pi over 6. So complement of pi over 3 is pi over 6. The supplement, so that's a similar kind of thing. You want the angle theta such that 5 pi over 6 plus this theta equals 180 degrees. So first of all, go ahead and change 180 degrees to radians. When you do, you're going to find out that it's pi. And 5 pi over 6 plus theta equals pi. You're going to solve for theta again, bring the 5 pi over 6 across. Pi minus 5 pi over 6 is pi over 6. So the supplement of 5 pi over 6 is pi over 6. Any questions so far? What we're solving. So going back to the question here, question asks for find the supplement of 5 pi over 6. Yeah, I know I'm moving a little bit quickly through it. I think that everybody probably knows what radians are and degrees, so I might be moving a little fast. I can slow down a little bit. So just going back up here, maybe complement and supplement isn't totally familiar. Complementary angles, those are two angles that they add up to make 90 degrees. So for example, 70 and 20 degrees, they add up to make 90 degrees. And supplementary angles, they're ones that add up to make 180 degrees. So the exercises that I was going through here was find the complement of pi over 3 and find the supplement of 5 pi over 6. So when we did the complement, we were looking for the angle theta such that pi over 3 plus this theta was equal to 90 degrees. Because complementary angles are ones that add to make 90. So we change 90 degrees to radians and then solve the equation this way. We bring the pi over 3 across and work our way down through it. Yeah, oh, this symbol. Okay, so is this symbol familiar to everybody? Can I get a yes or a no in the chat? Hey, Rosie, no worries, no worries. Theta, exactly, Stephen. Okay, good. So just like how we normally use x and y for variables that we're solving, like equations. When it's an angle, we often use the Greek letters. Theta is the most common one. That's almost like your x for angles. But we also use x for angles as well, so it's a bit funny. But it's pronounced, Stephen spelled it out there, that's useful. So theta, but being Irish, I don't pronounce my THs very well, so I'm probably going to train you badly here. But theta is how it's pronounced, with a THETA. It's a Greek letter. You might also see me using alpha, beta, other Greek letters for variables when I'm talking about angles as well. You'll probably also see me using x and y because it's also a habit, and you're gonna see lots of them as time goes on. So it's something to get used to. But yeah, theta. It looks like maybe I can zoom in here just so you can get a close look at the. So if you can see where it's shared there, it's a little bit like a zero with a line through it, but that's actually not how I usually write it when I'm writing the angle. You see me writing it soon enough, and I'll try to make a point to come back to the writing of it. But yeah, theta is just a variable. So I want to know, what do I add to pi over 3 to make 90 degrees? So it's like you said, I don't know what it is. Let that be x and then solve for x. I'm saying let that be theta, solve for theta. Yeah, so likewise with the supplementary angles, you're just creating a very small linear equation here and changing the degrees to radians and solving from there. So a few exercises here that definitely, if you're rusty, it'd be a good idea to run through them. These look like quiz level questions, easier than assignments, a little easier than final exams as well. I can see myself asking you to convert to radians or convert to degrees. Find the complement, find the supplement of this angle, and so on. I can see stuff like this appearing on your quiz this weekend. I haven't made it yet, so I might forget, and then you might not see it, so no guarantees. But as I'm looking at it right now, these look like good kind of multiple choice quiz questions to ask. Supplementary angles here. So definitely practice them, especially if you're rusty. Right angle trigonometry. Okay, so I think what I'm going to do is go back to my screen pen and everything. I'm just going to stop sharing here. I'll keep an eye on the textbook. I'm going to follow the textbook pretty closely, but I will go through it on the iPad here. Just takes me a second to get the broadcast going. There we go. Okay, so we are back in trigonometry now. Yeah, I know I went a little bit quickly through that section, but I think it's important to dedicate more time to some of the slightly harder stuff. So definitely have a good read over it, or if I went a little bit fast, check out the video and just hear me say something again. It might just help. Okay, so the first thing that comes to mind with right angle trigonometry are things like Pythagoras theorem and SOHCAHTOA. Hope that you remember SOHCAHTOA. So I'll just say recall SOHCAHTOA. It means sign opposite adjacent, and the SOA part of SOHCAHTOA comes from the first letters there. Cosine adjacent. Sorry, my bad. I'm making a dumb mistake already. Sine is opposite over hypotenuse, of course. SOH, not SOA. So sine opposite hypotenuse, cosine adjacent hypotenuse, and tangent opposite adjacent. So those are where the letters of that strange word SOHCAHTOA come from. SOHCAHTOA. And also what's going to be important for right angle trigonometry is Pythagoras' theorem, and we'll cover that in a second as well. Before we talk too much about sine and cosine, I guess I should just address what exactly opposite, adjacent, and hypotenuse are. So what are opposite, adjacent, and hypotenuse? Well, it only applies to right angle trigonometry, but let's say we have a triangle here with a right angle, and our sides are A, B, and C. And let's suppose we have an angle that we're considering in here called theta. Okay? So, considering the angle, oh, and I said I was going to kind of highlight theta for a second. I'm going to try to draw it slowly so you'll see how I write it. I kind of start up here, I come around in the top, and then I bring the line back through it that way. Considering the angle theta, opposite, which side is opposite the angle theta? B is opposite theta. The side that's adjacent to theta, I probably should have started with the hypotenuse, because the hypotenuse never changes. That's always going to be C, and this is always the longest side of the right angle triangle. The adjacent is going to be A. That's the side that touches the angle theta that is not the hypotenuse. The side touching theta that is not the hypotenuse. Okay? And if I was considering, let's say I did the same thing, right? I had a triangle like this here, right angle here, and I have A, B, and C. If I put my angle up here, and this time that symbol is alpha, in this case, C again is the hypotenuse. It's always the longest side, the side across from the right angle. This time, this time the opposite is A, and B is the adjacent. Last time, A was the adjacent, you can see, and B was the opposite. There you go, Max. Is that what you're looking for? Okay. So it's important to have a notion of, in your triangle, when you're looking at a right angle triangle, you want to be thinking about which side of the triangle is opposite to the angle that you're considering, which one is adjacent, and which one is your, wow, that's a horrific spelling of hypotenuse. Let me change that. Hypotenuse. No, it looks wrong to me. Anyway, it's important to know which is the opposite, which is the hypotenuse, and which is the adjacent, because that's how we're going to start off by defining sine, cosine, and tangent. Those functions that probably ring a bell from when you did trigonometry before, and hopefully more than just ring a bell, but I'll be going through them all again, making sure that everyone's up to speed on those. So, okay, this moves us on to sine, cosine, and tan, which are the basic trig ratios. Again, I'm going to draw another, sorry, my drawing isn't great today. Another triangle, another right angle triangle. So I'm going to put my angle theta, I'm going to put it back in here. This is going to be the side that is adjacent to theta. This is opposite to theta, and this side, of course, will be the hypotenuse. It's the one that's directly across from the right angle part. And so the definitions of sine, cosine, and tan, we're going to start by defining them. Sine is spelled S-I-N-E. Sine theta is the opposite over the hypotenuse. Cosine theta is the adjacent over the hypotenuse. And tan theta, and I'm just writing the full word above them here so that you have it as well. Tan theta is the opposite over the adjacent. Okay, those are our first definition of sine, cosine, and tangent, and we're going to extend that definition later. So just with a little bit of practice for them, let's look at a particular right angle triangle that you're probably going to see your professors use a lot because it has nice whole numbers in it. Doesn't happen with every right angle triangle, of course, but let's say this side is of length 3, this is a 4, and this is a 5. And again, I'm just going to put theta down here. This means that sine theta is the opposite. So I'm looking at this and thinking, and I've made a mistake. I'm looking at this triangle and thinking, sine theta is opposite over hypotenuse. So what side is opposite to theta? The 4 is opposite to theta. Cosine theta is adjacent over hypotenuse. Which side is the adjacent to theta? That's the 3. And tan theta is the opposite over the adjacent. So here we have adjacent, opposite, and the hypotenuse. Tan is the opposite over the adjacent. So that is 4 over 3. Okay? We're all comfortable enough with this much of sine, cosine, and tan so far? Can I get a couple of yeses, or let's go from 1 to 5. How do we feel about this preliminary kind of right angle definitions of sine, cosine, and tan? Okay, very good, very good. Okay, so here is where, so I'm satisfied that everyone's okay with that. What I'm guessing that a lot of people have trouble with, though, is the transition from sine, cosine, and tan being stuck inside a right angle triangle, where obviously the theta that you can see on the screen there is very limited. It can go from 0 degrees to 90 degrees. That's the only way that you can have that angle inside a right angle triangle. Usually in school, shortly after you learn about these right angle definitions, suddenly you're taking sine of 200 degrees or 100, and you're like, I thought sine lived inside the right angle triangle. Like, how are we suddenly taking sine of bigger angles like this. So this is where we move on to the unit circle. So apologies to anybody that feels like this is a little fast, but I'm thinking that most people are okay with SOHCAHTOA and the basic trig ratios in that way. So the unit circle, and we're also going to look at some special values. So what we're going to do is start by extending the definitions. Of sine, cosine, and tangent to angles on all the unit circle. Okay. So let me start again with a triangle, and then I'm going to kind of build around the triangle to hopefully have this make sense. Let me start with maybe a blue triangle in here. If I have a triangle like this, let's say I'm going to make the side of this one right here. I'm going to say that this is some length x, this is a length y, and this is a length theta. Or sorry, this angle is a size theta. Let's write that a little bit cleaner. Then what I can do is I can visualize this small right angle triangle, because again I have a right angle right here. I can visualize this inside a larger circle. So I'm trying to just draw in around it here. So let's say that this point right here, let's say that this is a point on the circle. Here's where I'm going to struggle to draw a nice circle, I think. Sorry for my drawing. You know, I actually need to improve that because I want to keep going with this. Sorry. I really want this to be a little bit better. Okay. It's not much better, but it is what it is. As I'm looking at that, I'm saying I can only see sine, cosine, and tangent fitting inside that first quadrant, that top right quadrant. But what we're going to do is extend it soon. Now, from this, I can say that sine of theta would be the opposite over the opposite over the hypotenuse. Cosine of theta will be the adjacent over the hypotenuse. So rewriting those again, x equals cosine theta and y equals sine theta. So inside in that first quadrant, that's going to be true, right? X is cosine theta and y is sine theta. And from our right angle triangle understanding, where we started off with a right angle triangle, an angle inside it, and opposite and the hypotenuse and all this kind of stuff, we're saying that really, really mirrors what we see inside this drawing that I've made here. The right angle triangle inside that first quadrant of the circle. But what I'm going to do is now say that we're going to extend the definitions, and tan will come soon, so tan is still there, but I'm just not talking about it just yet. Definitions of sine and cosine. so that they can act on angles outside the range 0 to 90 degrees or 0 to pi over 2 radians. Okay? Remember our interval notation, this would mean numbers between 0 and 90, not including 0 and 90, because originally when we talk about the right angle triangle, it wouldn't be a triangle if it was like a 0 degree kind of thing here, it'd just be kind of a line. Likewise, if we made it all the way up to 90, it wouldn't be a triangle as well, it would be back to a line again. So what we're going to do is extend it, and we're going to say that this is also going to work for angles outside. So what we have here, this here would be the point xy. It's actually cosine theta sine theta, based on what we just discussed. What we're going to say is that for angles bigger than 90 degrees, we can also just let x be cosine theta and y be sine theta and define them that way. This new definition that we're talking about is still consistent with what we built up inside the unit circle, but it now works outside of the unit circle as well. Okay? So maybe I can draw it on here actually. Let's say I have something going up to here, have an angle going from there to there like that, and let's say it's alpha. This would be cosine alpha sine alpha. Okay. If I had, maybe let's use green. Let's say an angle coming, getting a little bit messy, but all the way around from that initial side, the x side. Let's say this is a beta. The beta looks like a b with the thing extended. Then down here we would have cosine of beta sine of beta. Okay. So now cosine and sine work on angles that are bigger than 90 degrees. It's fine for us to do that because it's still totally consistent with what happens inside that triangle that we first built it up with. Okay. So the definition that we're now extending is what we're saying is for any x and y, or like pair that you're kind of considering on the unit circle, and it has a corresponding angle, right? Corresponding angle theta from the initial side, or x-axis, which is what we're going to be using. What we're saying then is that the x is equal to cosine theta and the y is equal to sine theta. Okay? That is how it changes. We build something that is still consistent with our original idea, but extends it to something better, something bigger. Tan is coming too. We won't forget about tan. Any questions so far? Okay, so if you have a question, feel free to type it. But I'm gonna keep going though. So what about tan theta? That one wasn't really there, right? We didn't really think about it, and sine and cosine kind of came out neatly as x and y, but tan sort of disappeared in all this. How is this used? Are we going to go through that? What this is used for? What it's used for? You're going to find these functions, sine and cosine, showing up in tons of areas of mathematics in university if you continue to study mathematics. They show up as solutions in differential equations in different settings. As I see your trouble. For now, it just seems like we're doing it for no reason, but you kind of need I need a whole class to go through or a whole course to go through. Oh no, you just don't know how we would solve them. Right, I haven't really done any questions yet. I've just kind of, I'll definitely get to that, don't worry. I'll definitely get to how you know, solve for theta if cosine theta equals this number, or solve for this number if theta equals some other angle. We'll definitely get to the solving of it. Yeah, I thought you were going a little bit more philosophical there, going, well, when would we ever use this? And it just comes up in math in different ways. Fourier series, pendulums, like all kinds of calculations that I'm not able to go through in this class right now. But I've covered them in tons of other classes I've taught. They show up in tons of areas of math. This is kind of the start of it, so I can't really get there. But yeah, no, we'll definitely cover like how to actually solve them and stuff. Right now I'm still in the building stage where I'm saying I'm still kind of trying to justify how do we get from sine and cosine inside of the right angle triangle to how sine and cosine are extended to the entire unit circle in that way. So we'll get there. We'll have lots of problems where we have to solve for angles inside sines and cosines and so on. Okay, so for now, what about tan theta? Okay, so notice that, let's say sine theta was the opposite over the hypotenuse and cosine theta was the adjacent over the hypotenuse. So sine theta over cosine theta would be opposite over hypotenuse divided by adjacent over hypotenuse, which would be opposite over hypotenuse. Remember, how do you divide a fraction by a fraction? You take the lower fraction, you flip it and multiply instead. Okay, those hypotenuses would cancel. You're left with opposite over the adjacent, which is equal to tan theta. So starting with sine theta over cosine theta, all along in our, when we were still in the right angle triangle scenario, tan theta was just sine over cosine. Well, that's also going to be how we define tan theta for when theta is not just an angle inside a right angle triangle. Theta can also be bigger angles too. So we're going to say that tan theta is just sine theta over cosine theta. Think of tan theta defined as from now on, rather than opposite over adjacent. Of course, if I ask you a question where we're living inside that little right angle triangle, and you have to do some little calculation in there, it's going to be more convenient to think of it as opposite over adjacent, but kind of more generally in trigonometry, tan is kind of defined as sine over cosine, okay? So, okay, are there any questions so far about how any of this is built? So, we'll definitely get to the kind of using it and solving problems and stuff soon enough. I'm still kind of in the building stage right now. Okay, now what we're going to start doing is building up the unit circle. So we're going to start with the unit circle properly now. So what are some key values on the unit circle? Let's say we have, yeah, that was a little better than some of my last attempts. So the first thing that sticks out to me are these ones here. When I see this, I would notice that that would be the point 1, 0. This would be the point 0, 1. This would be minus 1, 0. And this would be 0, minus 1. Now, I'm interested in those because those are immediately some values for sine theta and cosine theta that I just know based on looking at the unit circle, because, you know, we have I've sort of skimmed over it a little bit, but we have a rudimentary understanding of the size of angles. Like this here is 0 degrees, this would be 90 degrees or pi over 2 radians, this would be 180 degrees, this would be 270 degrees, like this. So some things that we know so far. So some special values we can see are that cosine of 0, that would be the x coordinate for when the angle is 0. Cosine of 0 is 1. Sine of 0 is 0. Okay. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of pi will be -1 because pi radians would be this one here. And remember, cosine is the x coordinate. So cosine of 180 degrees will be -1. And sine of 180, like that, will be 0. And, sorry, I was doing cosine first, wasn't I? Let's go to the next one. Cosine of 3 pi over 2 will be 0. And sine of 3 pi over 2 will be -1. So this time, I'm reading those from here. 3 pi over 2 radians would be this angle here. And cosine of 3 pi over 2 radians is the x coordinate, which is 0. And sine of 3 pi over 2 radians is the y coordinate, which is -1. So what I'm really trying to do right now is investigate cosine and sine. And once I know cosine and sine, I also know tan. So I'm not really talking too much about tan because it depends on cosine and sine anyway. What I'm trying to do is investigate as many special values of cosine and sine as I can right now and show where they come from. So again, I'm not really in a solving equations kind of stage yet, but I'm kind of discovering more things about cosine and sine as we look at angles that are not just in that first quadrant. Okay. So, you know, maybe on this diagram, I might just fill in a few other things here. This here would be pi over 2 or 90 degrees. This here would be pi or 180 degrees. And this would be 3 pi over 2 or 270 degrees if you come down this way. Okay. So that's where we're getting that from. Cosine of it will be the x coordinate associated with that angle. Sine of it will be the y coordinate. Okay, so can we find some other special values? Because I know that when a lot of you have done trigonometry, you seem to see pi over 4 come out, and pi over 6 and pi over 3. Two different values that are cosine equal. Well, because if cosine is the x coordinate on the unit circle, up here you have an x coordinate of 0. Okay, that didn't really mark. So up here you have an x coordinate of 0, and over here you have an x coordinate of 0. And most of the time, all the time actually, no, all the time? No, most of the time, definitely most, you will have cases where there are two angles that give you the same x coordinate or the same y coordinate, and that's something that that you're going to have to tackle, because when we're solving them, I know you probably still have another. Ooh, that's not a good sound. Please don't have a broken screen. Okay, it's not broken. Phone slid out of my pocket. Nobody likes to hear that. That little like heart in your mouth thing, and you're like, oh no, I broke my phone. What was I saying? Special values, yeah. So, oh yeah, so you probably have an eye ahead thinking of like, I remember I used to have to solve these things, and I might have to solve sine theta equals 1/2, but there will be two answers for theta. That's kind of what you're getting at with that question. Why are there two different values and so on? And we're definitely going to tackle questions like that as well. So yeah, not to worry. We'll get to all that too. But yeah, it's basically because the angles give you the same thing. You'll notice that there's also two ones where sine is 0. You have sine of 0 equals 0, but also sine of pi equals 0. And that's because sine is the y coordinate, and I can see two places, here and here on the unit circle, where the y coordinate would be at 0 because it's where the circle intersects the x-axis. That's something that you're going to happen. There's nothing wrong with that happening here. Now, what was it? So you're probably remembering from high school that pi over 4 seemed to be a special angle. Pi over 6, pi over 3. We were always talking about sine and cosine of pi over 3 and pi over 4, but not pi over 7 or pi over 8 or pi over 20. It was always pi over 3, 4, and 6, or even 2 pi over 3, 5 pi over 6, 4 pi over 3, 5 pi over 4. It was always over 3s, over 4s, and over 6s, whenever you had to kind of memorize angles and stuff. So I'm going to get to those and show like where they actually come from, not just more memorization to do. So let's look at this. More special angles. Okay, so consider the isosceles triangle below. So right now we're just going to start with a random isosceles triangle that looks like this. So it's a right angle triangle because that's how we have to start with sine and cosine whenever we're talking about triangles. Let's make this length 1, and I'm sure that you can see why I might do that, because now you're probably superimposing the unit circle in your head over it. If it's isosceles, these are the same lengths, and the angles are going to be the same size as well, because isosceles triangles, 2 of them have the same length, and therefore 2 have the same angle. So if we have 90 degrees in the bottom corner, that same angle is going to be 45 degrees. But like I said, I'm going to start using radians more often. So pi over 4 radians is equal to 45 degrees. That's what our isosceles triangle with a right angle in the corner will look like. So pi over 4 is an angle that kind of it comes out of an isosceles triangle like this, and you can do some calculations and figure out sine and cosine of pi over 4 quite naturally. So from Pythagoras' theorem, a squared plus a squared is equal to 1 squared. Remember how Pythagoras' theorem works? 2a squared is equal to 1. A squared is equal to 1 over 2. Then a can be plus or minus 1 over root 2. Now, obviously, we're not going to using the negative solution because we're talking about lengths here. So since a is clearly a positive length, we're talking about the length of the side of a triangle. It's not going to be negative. So our triangle then looks like this. We have a pi over 4, a pi over 4, a 1, a right angle. We have a 1 over root 2 here because that's a. This is also a, so that's also 1 over root 2. So let's just pick any one of these two here. I can tell you now that cosine of pi over 4 is 1 over root 2 divided by 1, the adjacent, divided by the hypotenuse, which is just 1 over root 2. That's actually where that comes from. So you probably used it before and been told by your teachers to memorize it because, you know, you might get asked a question or you're supposed to simplify or something. That's where it comes from. You can derive it from an isosceles triangle like that. And also sine of pi over 4 is also equal to 1 over root 2 as well. Same way. Sine would be the opposite over the hypotenuse, but the opposite is the same as the adjacent in an isosceles triangle. So sine and cosine is going to be the same. And tan of pi over 4, we might as well mention it here. It's going to be 1 because it's equal to sine pi over 4 divided by cosine pi over 4. Okay. Let me start from here. Some of the other special angles that you've seen, consider the equilateral triangle. Just make sure that I draw this one nicely. Bad drawing today. It's harder to draw on a glassy screen like an iPad than on paper. And let's make all the lengths of these sides equal to 1 here. Just tighten that up a little bit. So what are the angles inside an equilateral triangle? You might remember they're 60 degrees. So again, 60 degrees is, if you do the conversion, you're going to get pi over 3 radians. So for example, this here would be pi over 3, as would all the other angles. But what would happen if I drew a bisector down here? Well, that bisector cuts the angle in half. So you have pi over 6 up in here. That would create the right angle that I need to talk about sine and cosine. And that length there would be a half. And the length that we don't know, I guess, let's call it A. Okay? I don't know how long the bisector is. It's bisected the line at the bottom, so that line, we have a half on one side, we have 1 as the other thing. So let's quickly solve for A using Pythagoras' theorem. A squared plus a half squared should be equal to 1 squared. A squared is 1 minus a quarter, which is 3/4. And that means that our A that we're going to be using is root 3 over 2. So you remember that root 3 over 2 was probably a number that you saw a lot. So now what we have is this triangle here. We have a half. We have root 3 over 2. We have pi over 3. And we have pi over 6. And we have 1. So cosine of pi over 3 is the adjacent over the hypotenuse. Everything divided by 1 is always just going to be itself. So I'm going to leave out the over 1 part. Sine of pi over 3 is going to be root 3 over 2. Tan of pi over 3 is the opposite over the adjacent, root 3 over 2 divided by a half, which is going to be root 3. And we can also do pi over 6 as well. Cosine of pi over 6, this time this is the angle that we're looking at. The adjacent is root 3 over 2. Root 3 over 2 divided by 1 is root 3 over 2. The opposite is a half. And this time the opposite divided by adjacent. This time opposite is half divided by root 3 over 2. And you get 1 over root 3. Okay. So what we've done now with some kind of clever use of those kind of special triangles is we found out some values for angles pi over 4, pi over 3, and pi over 6. How I'm calculating them. Oh yeah, no worries. So cosine of theta, for example, is the adjacent over the hypotenuse. So when I'm doing cosine of pi over 3, I'm saying here's my pi over 3, adjacent to it is a half, hypotenuse is 1. So it's like a half divided by 1, which is equal to a half. Okay. That is what I'm doing for all of them. When it's sine, I'm doing it as opposite over hypotenuse. Yeah. Okay, so now we have a lot more special angles inside the unit circle. But as I was talking about, we're not just living inside the unit circle for sine and cosine anymore. Those are all extended to the entire unit circle. So God help me, I'm gonna have to try and draw big circle here with lots. This kind of looks accurate, so this might take me a minute. I think if I draw the circle first, it'll probably be easier. I'm gonna draw it in blue. That could have been worse. I think I'll try one more time. No. Keep making it too short at the bottom here. Okay. That's about the best one I've done, I think. Let's draw in a kind of a lighter color for the axes here. About there, I would say. Yeah, that could have been a lot worse. I'll take that. This is your X and your Y. So what we've discovered, for example, is that pi over 4, the very first one we did, that's 45 degrees. That would be going up to there. If that's pi over 4 degrees, we found out that sine of pi over 4 was 1 over, cosine was 1 over root 2, and sine was 1 over root 2. And sometimes that's also the same as root 2 over 2. You might have also learned it as root 2 over 2. So same thing. I have, by using the symmetry of the circle, like I'm trying to do now, except I'm not very good at drawing, so my circle is not all that symmetric. But if I kind of translate that all around by symmetry, I can say that this number over here will be minus 1 over root 2 and 1 over root 2. This one down here will have both of them negative. And down here, it's just going to be the y coordinate that's negative, right? I can also figure out what a bunch of these angles are going to be. Okay, so we did this earlier, right? We know that cosine of pi over 4, what have I done? Cosine of pi over 4 is 1 over root 2. And sine of pi over 4 is 1 over root 2. That is how I got those there, okay? So what I also need to know is what is that angle? What is that angle there? And what is, how many colors have I got? Let's go with orange. What is this angle all the way around to here? Because if I know what those angles are, then I also know what sine and cosine are of those angles, because I know that the cosine of whatever angle that would be this one, the sine would be that one, cosine is this one, sine is that one, and so on for the different angles. Maybe I'll use this as kind of color coordinated here. So let's start with the first one. If this is all done symmetric and done well, okay, this is going to get very messy, but I hope that you're following live and you can see when the different mess gets added. If this was a picture at the end, it would be horrible. This angle here is going to be pi over 4, right? Because that's going to be like a mirror image of the thing, the way it gets flipped across by the symmetry of the whole situation. But I'm more interested in what the angle is of that red line, not that one. So to get the angle, I know the full way around to the other side of the x-axis. That's going to be 180 degrees or pi radians. So the red part that I want is pi minus pi over 4, which is 3 pi over 4. So this red part, just taking it away from there because it was going to get messy, I think. That's 3 pi over 4, okay? So this means that, and these coordinates that I had up here, this was minus 1 over root 2 and 1 over root 2. This means that cosine of 3 pi over 4 must be minus 1 over root 2, and sine of 3 pi over 4 is equal to plus 1 over root 2. So now you're seeing that I have two angles, Evan, you mentioned earlier. I have two different angles to give you the same number for cosine. For sine, sorry. Sine of pi over 4 is 1 over root 2. Sine of 3 pi over 4 is also 1 over root 2, because there's two heights where the y coordinate is going to be the same by the symmetry of the thing. Okay, so I think I've tried hard enough to keep drawing and stuff here. So what I'm going to do is, you can read about all this in the textbook as well. That's one taste of it. But did you understand the red angle? Oh, no worries, no worries. So the red angle, that was this red angle here. What I know from the way I drew it, by the symmetry, this was pi over 4 because the other side was pi over 4, and I kind of mirror imaged it across. Now, if the whole way around is 180 degrees, this would be pi radians. Then the red angle that make sense? Okay. One more angle as well, actually. The blue angle, if you look above, that was, whoops. After all that kind of translating around, the blue angle was coming around to here. So by the symmetry of the whole situation, I should have a pi over 4 in there, right? Because I started off with pi over 4 here, and I ended up going down and across and everywhere else. So that there should be pi over 4. So what does that make the blue angle? Well, how am I going to get that? It's going to be, I can go as far as pi, and then I can add the pi over 4. That would be pi plus pi over 4, which is 5 pi over 4. And now I know what cosine of 5 pi over 4 is, and what sine of 5 pi over 4 is. I have more special angles for cosine and sine, and therefore for tan as well, because I just have to do sine divided by cosine. Okay. And you're going to do the same thing in the final quadrant, except, you know what, maybe I should just show it. A little slower than I meant to here, but the last one was down here. The angle I want, what color did I use? Orange. So for the orange angle, this one went all the way around here. Again, like I said, I started off with this angle. It was pi over 4. By that kind of mirror reflection thing, this is pi over 4. So what I do know, though, is if I went the full circuit around, it would be 2 pi. So what I'm going to do is just say that it's 2 pi minus that angle that I have to, that's down there. And I get 7 pi over 4. Okay. That's where all those come from. Okay. So I'm going to stop sharing here for a second and go back to the book because I've done it in there too. If you do that for all of those angles that we developed, right? We figured out pi over 6, pi over 4, pi over 3. If you translate all of them around and superimpose them all onto the same thing, you filled out a unit circle like this with lots and lots of angles, and with lots and lots of different special values. Now, there's going to be some memorization involved. You're going to end up memorizing the ones in the first quadrant and then using some things like, I know that sine is positive here, tan and cosine and so on. You can use some other techniques to figure out what the other angles are going to be and what the sine and cosine of those other angles are going to be, or what all the options are. For example, to have the y coordinate of root 2 over 2 or the x coordinate of let's say half, these ones down here. So if you do that to everything, we pretty much just did that for pi over 4 on the board there. We said, okay, I have root 2 over 2. I'm going to kind of mirror image that one across here. And I get minus root 2. All that happens is the x coordinate changes. I'm going to flip that down below. Both of them are negative. And over here, the x coordinate is positive and the y coordinate is negative. And we worked out what those angles were on the board as well. It's like doing that for pi over 6 and pi over 3. I'm putting them all onto the same thing here, onto this unit circle diagram. Okay, are there any questions? So, can I get 1s to 5s? How are we feeling about this stuff? Again, I haven't showed you how to like answer a question yet. This is all the background of kind of where it all comes from. I just suspect that this stuff is glossed over a lot in schools, kind of, and you're given stuff to memorize, but or at least I was when I was taught, and I didn't really know what I was doing. I didn't really know where, you know, sine of pi over 3 ever came from. I was just told it's root 3 over 2 and to learn it. So I like to make sure that I go through the whys with everybody when I do it. Okay, so anybody else? Can anybody else comment here? It's decent so far. There's a lot of it here in the book you can read through. Even the stuff that we did with. So I did pi over 4 in class there, but you can see the one for pi over 6 in here as well. At some point we derived that cosine of pi over 6 is root 3 over 2, sine of pi over 6 is a half. If you translate that around, you're going to get these coordinates on the unit circle that are kind of opposite and across from it and so on. And you can see where the pi over 6s are going to end up and figure out that this would be 5 pi over 6, that's 7 pi over 6, that's 11 pi over 6 if you do the same calculation I did. And when you bring it all together, you're going to end up with your 5 pi over 6, your 7 pi over 6. You get all in the same thing here. Are there any questions? We'll be getting to some of the example-y kind of questions now where I ask, what is this and what is that? And you have to do a calculation. So I think I'm done torturing you with the theory behind it right now. We should be moving on to, if I can remember correctly, some examples. We can skip over this. Yeah, so the explanation is all here, but I think I'm going to go back to the screen and do a couple of examples with you before the end. So what's in here is going to be a little longer than what I'm going to explain in class, because it is the more technically perfect for any angle that you're working with, regardless of it being a special angle, one of the pi over 3, one of the over 3s, over 4s, over 6s. This is what you would need to do. But we're only going to work with the special ones because you need calculators for anything else. So I can give you some quick strategies to solve for special ones. So I think we're going to end on something that you're not going to find too hard here. Again, if there's any questions, don't forget, just ask. Okay, so finally, we're going on to some kind of examples that you might be asked to do in a quiz or a test or something. Okay, so in the textbook, there was a few here. There's cosine of question was to evaluate following. And the first example was cosine of 2 pi over 3. So basically how this works is memorize the results from quadrant 1. That is that cosine of pi over 3, sine pi over 3, cosine pi over 4, sine pi over 4, and cosine pi over 6, and sine of pi over 6. So from whatever technique you prefer, figure out a way to do it yourself, or I'll probably end up suggesting things as we go along, but you want to have those memorized, okay? Because if we're going to tackle something like the cosine of 2 pi over 3 up there, or cosine of 5 pi over 6, or 11 pi over 6, whatever it might be, what we're going to do is work out a way to relate that special angle that's outside of quadrant 1 back to the corresponding angle that we started with to get to that angle with the kind of mirror vision thing we did, where we were kind of translating along the mirror image to the other quadrants. So whenever you see an angle outside of these first quadrants, we're going to try to relate it back to the other one and go from there. So you might remember this was 1 over root 2, this was 1 over root 2, or if you like, root 2 over 2. Cosine of pi over 3 was... So how I always remember it, for some reason I always remember sine of pi over 6 as a half. That means that the cosine must be root 3 over 2, and it's the other way around for the other ones. Cosine of pi over 3 is a half, sine of pi over 3 is root 3 over 2. Okay, these ones are memorized. So back to the problem at hand, cosine of 2 pi over 3. The trick is to drop that number there, the one on top. No, those are fixed. The ones, if you mean these here, those are always going to be fixed. They'll be the same no matter what the question is. What we derived earlier won't change. Those ones are always fixed, but what you're asked might be different. So like now we're doing 2 pi over 3, and you have to figure out your way back to one of those key angles. Okay, so the trick here is to drop this number drop the number in the numerator, and I should say that is not pi, the number that's not pi. For a second, what's going to be different? Yeah, Eric, that's the exact same thing. So 1 over root 2, if you multiply it by root 2 over root 2, you get root 2 times 1, and then root 2 multiplied by root 2 is 2. So you're totally fine to use whichever version of it that you want. Yeah. Okay. So one thing to remember that you might have realized in this unit circle stuff that we talked about. Does this ring a bell with anybody? A triangle like this? And get a yes or a no in the chat. Very good. Everybody else? Good, good. So this kind of fell out of all the work that we did. What it means is, just for anybody that's maybe thinking no but doesn't want to say it since everybody else said yes, A means all, S is sine, T is tan, and C is cosine. Now what it means is that in that first quadrant, all of the trig functions that we're working with are positive in there. In the second quadrant, where the S is, sine is the only trig function that is positive. In the third quadrant, where T is, tan is the only one. What numbers? Which numbers are you talking about? In the third quadrant, tan is the only one that's positive. And in the fourth quadrant, cosine is the only one that's positive. That list in yellow, those are the things we solved with the triangles back here. Remember when we got all these? Cosine of pi over 3 was a half. Cosine of pi over 6 was 3 over 2. We solved all those back there. But if you have the PDF of the textbook handy, or if you have it open, you can go to page 128, and I have a table of it all put together there as well that you can check out. Okay. And we also did it for these ones here. We did the isosceles triangle, we found 1 over root 2, and we found sine and cosine of pi over 4 as well. Okay. So what we have to decide is, which quadrant is 2 pi over 3 in? Okay. Because that's going to tell us whether the sign should be plus or minus as we try to calculate. So which quadrant is 2 pi over 3 in? Can anybody say, is it in quadrant 1? Oh no, I think my pen is running out of battery. That is no good. 1, 2, 3, or 4. So in the chat, 1, 2, 3, or 4, which quadrant is the angle 2 pi over 3 in? We don't know. Not in 1. Anybody else? Okay, think again about your radians. Eric says 2, Ayush says 2. Okay, good. So let's look at these angles here. This is pi over 2 radians. This would be pi radians, and this would be 3 pi over 2 radians, yeah? So 2 pi over 3, where would that be? You're right, it'll be in quadrant 2. Because 2/3 is between a half and 1. The half that I'm talking about is coming from this. Oh no, pen is definitely going. That's bad timing. Can I charge it for a minute there? So when I said it's between a half and 1, it's because the half, what I'm looking at, is coming from the pi over 2 radians going straight up, the 1 over 2. And the pi radians, that's just 1. 2 over 3 is between a half and 1. So the angle 2 pi over 3 is in that second quadrant. Now in that second quadrant, going by that little chart that we have, sine is the only, it's the only trig function that's positive in there. Cosine is negative. So when we do it, my pen is dead. I'm gonna have to switch over to my laptop screen here instead of this. So just bear with me for a second here. Okay, I'm just going to stop sharing on the iPad. Okay. And hopefully you can find my laptop. It's over there. Just turn this over. Okay, so let me share. This window right here. Okay, so where was I on the iPad? Let me just see. I think I was somewhere like cosine of 2 pi over 3. We were talking about this thing here. We determined that 2 pi over 3 is somewhere in here. Sine is the only positive thing. And the technique that I want you to use is to drop this number and then use the fact that since sine is the only positive trig function in that quadrant, this must be negative. You've memorized that cosine of pi over 3 is 1/2, so the answer is 1/2. We derived cosine of pi over 3, cosine pi over 6, cosine pi over 4, and also sine of all them earlier in the class. And now we're going from memory on those because we have to memorize the ones in the first quadrant and use what we've memorized to work out what they are in other quadrants. So another one here is, this was question 1. Question 2 on that example was sine of 7 pi over 6. Again, what I want you to do is so if it doesn't say sine in front, it would be negative because only sine would be positive. Can you rephrase that one for me? I don't follow the question. Maybe unmute if you like, it might be easier. Cosine is negative, so in this thing over here, we have this kind of rule that sort of comes out that all of the trig functions are positive when the angle is in this quadrant. Sine is the only one that's positive when the angle is in here. Tan is the only one that's positive when the angle is in here. And cosine is the only one that's positive when the angle is in here. We determined that 2 pi over 3 was in this quadrant. Since sine is the only one that's positive in that quadrant, then cosine is negative in there. So that's why we had the minus sign. Okay. Okay, so doing sine of 7 pi over 6. Yeah, I know it's tricky. Some people have it well and some people don't. Whoa, what happened there? Midterm covers up the rational numbers. This must have been an old. Let me stop sharing for a sec. Or to use the iPad. Okay, yeah, there it is. Okay, I'm just going to keep you a minute over time here since we got a bit interrupted. Sine of 7 pi over 6. So my thought is, where is 7 pi over 6? Can anybody answer this one for me? Sooner people answer, the sooner I get through it. Which quadrant? A, S, T, or C? Where would you find 7 pi over 6? T, very good. Because 7 pi over 6, 6 pi over 6 would be pi, right? And that's where pi is. I want this right. So 7 pi over 6 is going to be just extended into the next quadrant. Now, tan is the only one that's positive in there, meaning that sine is negative. And you drop that 7 on top. You've memorized what sine of pi over 6 is. It's a half. So this answer is actually also minus a half. Okay? Any questions here? One more here. So this is probably something I'm going to put on your quiz. Tan of 5 pi over 4. Again, I'm inclined to put this to the side somewhere. Where would 5 pi over 4 be? A, S, T, or C? Again, think of pi radians this way. 3, exactly, Eric. That would be this one here. Tan is positive in there. So when I drop that 5, I don't add the minus sign, because that's the quadrant where all the tans are positive. And tan of pi over 4 is 1. So 1 is your answer for that one. Okay? If anyone's a little shaky on this, feel free to send me an email. I'll happily set up a call for us to talk about it more. Because I'm likely going to put something like this. This is a nice little short question for a quiz that I'll probably put on your quiz this weekend or this Friday. So, don't let it go by without being just going, that was late in class and I'm tired and I didn't really listen. Definitely take the time to work through it. And if there's something that you don't get as you're reviewing this, because like I said, it's the end of class and maybe you're a bit tired, feel free to send me an email and we can set up a time to discuss it. Okay? Okay, I'll let you go then, and we will pick it up from there next week as well. Anybody in the academic coaching, I'll see you soon at 2 o'clock. Okay, take care everyone. Bye-bye.